For as long as we've had planes, we've had pilot error. It's been the go-to explanation for some of aviation's worst disasters. And for decades, the industry has basically declared war on it, pouring millions into designing smarter and smarter systems to make flying safer. But what if? What if in trying to solve that one problem, we actually accidentally created a whole new one? That's the question we're digging into today.
Just listen to those words. What's the plane doing? That is a phrase you never, ever want to hear from the cockpit, because it means the pilots aren't in control. Suddenly, they're just like the rest of us in the back. Passengers, desperately trying to figure out why their own aircraft has decided to go rogue. So, picture this, a routine flight, Singapore to Perth. It's on this super modern plane just packed with the latest safety tech. And then, out of nowhere, it pitches down, all on its own. It climbs, and then it plunges 650 feet. Then it does it again. In the cabin, it was absolute chaos. And in the cockpit, just confusion. The very systems designed to prevent a crash were now seemingly trying to cause one.
And that leads us to this really terrifying question, which is at the heart of what we're talking about today. How is that even possible? To really get it, we have to rewind the clock, back to a classic, tragic mistake that ended up shaping the industry's response for decades. Okay, so the year is 1989. We're in the United Kingdom, and the flight is British Midland 92. This is the story of what should have been a straightforward emergency, but it turned into a complete catastrophe because of a simple, very human misunderstanding.
So, the crew, they're experienced pilots. And as the plane starts shaking and smoke starts seeping into the cockpit, they immediately think, engine failure. Okay, they've got a 50-50 choice to make. Is it the left engine or the right one? Get it right, they land safely. Get it wrong, well.
And here is the trap they fell into. See, these guys had spent their entire careers flying older 737s. And on those old planes, their experience told them two things. First, the air conditioning, where they thought the smoke was coming from, was fed by the right engine. And second, the little vibration dials, notoriously unreliable. But this was a brand new 737-400. And on this plane, both of those things had changed. The aircon was now fed by both engines, and those new vibration instruments were perfectly accurate.
So, trusting his gut, trusting his years of old experience over the new instruments right in front of him, the first officer makes the call. Based on the smoke and what he knew about the older planes, he's absolutely certain the problem is the right engine. Meanwhile, the vibration dials are practically screaming at him that it's the left engine that's on fire. But he ignores them. And that was the fatal decision. They shut down the perfectly good right engine. They were now relying on the damaged, burning left engine to get them to the airport. And, well, it didn't make it. That second engine failed on final approach, and the plane crashed right onto the M1 motorway. A disaster like the one at Kegworth obviously forces the industry to react, and it did. It led to a whole series of logical, well-intentioned changes, all designed to stop these kinds of mistakes from ever happening again. You can really see how the industry reacted over time here. Back in '72, a crash happened probably because the captain was distracted by an argument. So they made a new rule, the junior first officer flies, which frees up the more experienced captain to just monitor everything. Then, after Kegworth in '89, the solution seemed obvious, right? Pilots needed more and better simulator training to really learn the differences between all these new planes. More training, better procedures, it all makes perfect sense, right? Well, fast forward to New York in 2001. The crash of American Airlines 587 would show in the most tragic way how those very solutions could actually become part of the problem.
So, shortly after takeoff, Flight 587 hit something called a wake vortex from a jumbo jet that took off right in front of it. The easiest way to think about it is like hitting the wake from a massive boat, but you're in the air. It's a common thing, it's predictable, and pilots train for it all the time. But what happened next was anything but common.
Responding to that turbulence, the first officer, Sten Mullen, basically stomped on the rudder pedals. But he did it with incredible force, swinging the rudder all the way from full left to full right, back and forth 4 times in just 7 seconds. These movements put so much stress on the tail fin, literally twice what it was designed to handle, that it just snapped off. So the million-dollar question is, why did he do that? Well, just look at how all those previous fixes played a role. First, as the junior officer, he was the one at the controls, exactly like that post-1972 procedure said he should be.
Second, investigators found that his simulator training actually encouraged pilots to be really aggressive with the rudder. And this is the kicker. American Airlines had never, ever warned its pilots that it was even possible to break the tail off this way. The whole system of fixes had unintentionally created a brand new fatal trap.
So, after a tragedy like that, the industry goes for an even bigger, more ambitious solution. If new procedures and better training aren't enough, what if you could just design the human out of the equation altogether? What if you could build a plane that was, well, pilot-proof?
And this led to the philosophy that Airbus really pioneered with its fly-by-wire system. The idea is the pilot's controls aren't directly connected to the wings and tail anymore. Instead, when a pilot moves the stick, they're really just making a request to a computer. And it's the computer that decides the best and safest way to do it. So if a pilot tries to do something dangerous, like pull up way too steeply or bank too hard, the computer will just say, nope, and protect the plane from itself.
This quote really just says it all, doesn't it? The goal was to build this sort of electronic cage around the aircraft, a set of hard limits that a pilot could never break, no matter what kind of mistake they made. It was seen as the ultimate technological fix for a human problem. And that brings us full circle, right back to Qantas Flight 72 hurtling towards the ocean. Because what we learned is that this ultimate solution, well, it created a brand new, more subtle, and you could argue, an even more dangerous set of problems.
This question has become strangely common in the age of the super-automated cockpit, and it shows this fundamental disconnect that can happen between the pilot and the plane. When everything's working, it's amazing, it's seamless. But when the automation has a glitch, the pilot isn't really a pilot anymore. They're a troubleshooter, trying to diagnose a complex computer failure while flying at 500 miles an hour.
Just look at these two incidents side by side. In both cases, a simple little sensor failed and sent bad data into the system. For Qantas 72, it caused those terrifying dives. For Air France 447, it led to airspeed readings that were all over the place, and it confused the pilots so badly that they completely lost track of what the plane was actually doing, and they stalled it all the way into the Atlantic. They got so fixated on trying to solve the instrument problem, they forgot to actually fly the airplane.
And that, right there, is the automation paradox. We haven't gotten rid of pilot error. We've just changed what it looks like. The new pilot error isn't about misreading an engine fire. It's about being unable to figure out what the computer is doing and why it's doing it in the most crucial seconds of an emergency. When you look at it this way, the pattern becomes crystal clear. Each logical fix, from new procedures to better training to revolutionary automation, it solved one problem only to accidentally create the perfect conditions for a new, unforeseen kind of disaster. And that leaves us with this huge question for the future of flying. We have made planes that can fly themselves brilliantly, like 99.9% of the time. But what about that tiny fraction of a percent when it all goes wrong? Are we really preparing our pilots to take back control when the ghost in the machine suddenly decides to go rogue?